Alrighty. So yesterday we were talking about how when it went, we were trying to lift it up here, right? And that was really hard, really dangerous. Probably not the best situation in any way, shape, or form, right? And so our traveling inventor guy came and suggested they build giant ramps out of earth. Yeah? Remember that?
Dirt, basically?
Yep. Giant, dirt piles.
How long did it take them to make that?
What if it crumbles?
I mean, they had like 20 or 30 of these, so.
Yeah.
I mean, I would imagine that this is way less likely to fall over than that.
So does that mean it's like worth a lot? They're doing a lot.
Yeah, how much did it cost on all?
I imagine that these mammoths are selling for quite a bit.
I need a time frame of like when this is. Like, why don't they just get a crane?
So it's in the time of the caveman.
Okay.
So, and this traveling inventor is traveling around telling people about simple machines.
There's traveling inventors in caveman times.
Apparently.
Time traveling.
The
Yeah.
Time traveling inventors.
Oh, it might be a time traveling inventor. And he's just trying not to blow their minds too much. Yeah. All right. So we said that having this nice earthen ramp would help with our how hard it is to get the boulder up to the top, right? Yeah. We said that this was a simple machine. Which simple machine was it?
Incline plane.
An incline plane. Okay. So before we said that all simple machines are going to have this trade-off of force and distance, just like our levers did. Do you guys remember this?
Yes.
Vaguely, sort of. Okay. So, what distance do you think we're trading off here?
So like, what does that mean?
So,
Height?
we know that it should be easier to push this up the slope, right? Yeah. If we push it up the slope, is our boulder going to have to move a larger distance than if it goes straight up?
Yes.
Yeah. So we can kind of see that we can pretty easily see our force distance trade-off, right? We've got a longer distance our boulder travels, but we don't have to push as hard. Kind of make sense? Yeah? Okay. Now, our equation is going to work exactly the same as before, right? But I want to kind of diagram this and show you how it works. But first, do you want to finish the story?
Yes.
Okay. So, we just read the part where he informs them of how to build the ramp, and then they can roll it up with a lot less force. Yeah? All right, so we've got one paragraph left. You ready?
Yes.
At first, the simplicity of my solution was greeted with understandable skepticism. What do we do with the towers? They asked. I made a few more calculations and then suggested commercial and retail developments on the lower levels and luxury apartments above.
Yeah, definitely.
So what is he suggesting? They pretty much make apartment buildings like we have now, right? In big cities. So like New York, it's like all shops and stuff along the bottom, but then apartments up top. Yeah. So that's pretty much what he's suggesting they do with the old Mammoth Towers. Cool? Okay. All right. So we still need to kind of talk about how we solve problems with this and figure out how much easier it is to roll this boulder up the incline, right? So for this, we need to figure out a few other variables, right? So let's say we know the weight of the boulder. So what's the weight of our boulder?
200 pounds.
Let's keep it in newtons.
I don't know. 100.
You want me to convert it for you? Okay. Let's see here. So it would be 889.644. So you want like 890 or something like that?
Yes.
Okay. So we have 890 newtons. Okay. First thing you should notice is this was 200 pounds and we have 890 newtons. So newtons are significantly smaller. Okay. 200 pounds would not be a unreasonable value for the weight of a larger adult male, right? Yeah. So it would not be completely out of the question for somebody to have a weight of 900 to 1,000 newtons. Okay. So newtons are a lot smaller. So if we have a problem where we're doing, I don't know, an average person, and I say their weight is 600 newtons, that's actually a pretty average sized person, probably on the small side of average. Cool? Just to kind of give you guys a scale with the newtons. All right, so we have an 800 Newton boulder. That means that if we tried to lift it up, we would have to lift with at least 800 newtons to lift it up, right? Or 890, sorry, 890. Cool? All right. Then, let's see. Let's say that because they had to build these ramps specifically for this, they did a few tests before they built the ramp, okay? So let's say that they went through and they tested the mammoth casters to see how much force they could apply, okay, and how hard they could push the boulders. So what force do you think they got? Let's figure that out. Let's just make up a number. 600 newtons. So this guy here can push with 600 newtons up the ramp. Okay? Now, what we can do is we can actually look at this and say, okay, we know that if we lifted it directly up, 890 newtons would be the force we'd have to apply, right? And we know the height of our ramp or the height of our towers was 20 meters. So we know we need our ramp to be 20 meters. Now, since we know all that information, if we're doing force times distance, we only have one variable that we don't know, and that's the length of the ramp, right? So what our traveling inventor probably would have done is say, okay, you can apply 600 newtons by yourself. So we're going to make this ramp so that one person can roll most of these boulders up the ramp. Sound good? All right, so like I said, we're going to set this up just like for the levers, because that same equation is going to work for all our simple machines. So we have that same equation. Force 1, distance 1 equals force 2, distance 2. Good? All right. For an inclined plane, your force in your distance, or one of these forces in distance, is going to be the vertical side. Okay? So this side is going to be, what if you were lifting it directly upward? Okay? So we're going to have our 20 meters times our 890 newtons. And then on this side, it's going to be the force that you have to apply, so the 600 newtons, times the distance it would go. Okay? So we have 600 newtons times our distance. Just D in this case because we don't know what it is. Good? Any questions? No? All right. So we're going to solve this just like before. Divide both sides by 600. Anybody have their calculator out yet? Apparently you guys aren't going very quickly with your calculator.
I had it.
Okay. So our distance is 29.67 meters. So this is not that much longer than our 20 meters, right? So this ramp's still going to be pretty steep. So they might want to make it a little less steep just so that it's a little easier to walk up, right? Because this is going to be fairly hard to walk up a slope that steep. Cool? Any questions? No? You guys pretty good with this? All right, I did want to talk a little bit about why we can set this equal. Because with a lever, right, you're pushing on one side and the other side is pushing up, right? Yeah? So it's really clear to see we're putting energy in over here and getting that same energy out over here. Yeah? Here, we're not pushing on anything, right? If we're rolling this boulder up, this side here is completely imaginary. We're not lifting the boulder up at the same time, right? So where is this equal energy coming from? Okay, because work is energy. We went over this last with the levers. So work is energy. Where is this idea of these equal energies coming from? And this is actually coming from something called gravitational potential energy. Okay? And this is the energy something has by how high you lift it up off the ground. So if I hold the marker here, it's got some amount of energy. If I lift it up higher, it's going to have more energy. Okay? And this is the energy that's going to turn into kinetic energy or energy of motion as it falls. So if I drop it from here, it's going to hit the ground faster than if I drop it from down here. Does that kind of make sense? So the energy that we're really looking at being equal here is our gravitational potential energy. And gravitational potential energy is kind of special because it acts a lot like the energy we had with our lever. Okay? So we move this side a certain distance, and this side may move less or more depending on where our fulcrum is. But we get the same amount of energy out as what we put in. With our gravitational potential energy, we will always have the same amount of energy as long as we move something to the same height. Okay? So whether we lift it up from here to here, or we roll it up a really long incline, we're still lifting it to the same height. So we've had that same change in gravitational potential energy. Does that kind of make sense? Yeah? So that's where our equal work done is coming from. It comes from the height you are up off the ground. Any questions? No? Okay. Cool. I'm going to pause this one here.